this kind of guy. Okay? That's f d alpha j minus d alpha of fj. When you look at the action of this commutator on the function j, it satisfies the following estimate. The L2 norm is less than the constant times what? Times the gradient of f in n infinity times the norm of j in hs minus 1 plus this is the other term, the norm of f in hs, the norm of j in n infinity. So I don't have time to prove this inequality, but it's easy to understand where it comes from. In this term here, okay, you have a bunch of terms, okay? But what are the extreme cases? Okay? Extreme case in this commutator is the case where one derivative hits the f and all others hit the j. This gives you can control by this. And the other extreme case is when all derivatives hit the f, which can then be controlled by this guy. So for a complete proof, you can see the book by Maida and Bertozzi, or my lecture notes in French. Okay, consequence of this commutator estimate. On our energy estimate, so you see that we have that 1/2 of d over dt of hs squared will be less than, so I apply the commutator estimate for this guy. I will have a constant. I will have the gradient of un in L infinity, the gradient of un in hs minus 1, plus un in hs and the gradient of un in L infinity. Okay. And I multiply this by d alpha un in L2. This guy is the same as here, and this controls that. So this is less than constant, the norm of gradient un in L infinity, and all of the guys I can control by norm of un hs squared. Alright. So that's the right hand side that appeared in the proposition. So then I sum, sorry, here this is d alpha un, sorry. This is d alpha un in n2. Sorry, this is d alpha un in n2. Okay? And then I sum over all alphas to get the result. Alright, so this is the crucial energy estimate. And the main point is you get rid of the worst term by the constellation property, and the other terms are nicer, and you control them by this nice estimate. Okay, so that's for the proposition. What about the corollary? So I will leave it to you as an exercise. You can deduce from this the bound that I mentioned. I will just give you a hint. You see that in the estimate of the proposition, you have this norm, this L infinity norm of the gradient. So that's why, again, S needs to be greater than that. Okay? Because for S greater than t over 2 plus 1, you can use the Sobolev embedding and it will give you that the L infinity norm of gradient of un is less than the constant times un in hs. Right? So when you use this Sobolev embedding here, you see that the function phi of t, which is the hs norm of u of t squared, satisfies phi prime is less than constant phi to the 3/2. Right? Because you see, here I will have phi, and here when I use the Sobolev embedding, I have the hs norm cubed. Okay, so the square is to the power of 3/2. So you have this inequality here implies this kind of inequality, and you know that for this ODE you have a local control in time. Okay, so that's why you can get from here the uniform bound, uniform control locally in time. Okay, then you have to work to make everything rigorous. Okay, but the underlying inequality is this one. Okay, and it also explains to you why it's only local in time, because you see this ODE phi prime equal phi to the 3 half has solutions only locally in time. As soon as you have phi prime equal phi to the alpha with alpha strictly greater than 1, you have blow up. So that's why if we don't do better than that, we cannot expect more than a local in time result. That's it. Okay, I'm almost done with this long proof. We had these approximations. We have uniform bound. Last step is compactness, or at least convergence, when capital N goes to infinity. Last step is the convergence argument. So, from the corollary of step 2, you can show the following proposition. Un is a Cauchy sequence in